So we've seen FSK, frequency shift keying, before, and in the previous incarnation we saw it with coherent detection. Now we're going to talk about how we can also do detection effectively with non-coherent detection. Of course, the motivation for doing non-coherent detection is to lower the cost of the system. So coherent systems require a phase-locked loop that tracks the phase of the two oscillators, the transmitter and receiver, to keep them in sync. And non-coherent detection is predicated on an approach that simply doesn't need the phase information. And since it doesn't need it, you don't have to have this tracker. Of course, there's something that we have to pay, and this time the pay is not in the cost of the system. We're reducing the cost. However, the performance of the system will be somewhat degraded because we're using a lower cost solution. So let's see, how does this non-coherent FSK work? So first, let's start with the coherent receiver. And in the coherent receiver here, we have M branches because it's an M-dimensional space. So for M-FSK, we have M dimensions, and there are M branches. Each one of the branches does a correlation with the symbol. And in this case, because it's an orthogonal modulation format, we know that the symbols are basically equal to the basis vectors. The only difference is a normalization. So here, essentially, we're correlating with the basis vectors, or we're correlating with the symbols. For M-FSK comes to the same. And each one of these correlations requires knowledge of the phase. So let's say that each one is a cosine omega I of t. So we have a different frequency for each one, frequency shift keying. And each one has got a different oscillator. It's got a different phase of the transmitter and the receiver. And if we want to get perfect coherent detection, of course, we need for these phases to be aligned so that that goes to 0. So we have a phase-locked loop which forces this to 0. Now, I'm looking for a solution where I don't need this. So I'm going to have to change the structure of my receiver. Now, for this receiver, we used our approximation coming from the union bound in order to come up with this probability of error. And this is going to change when we change the receiver structure, because this equation is based on this strategy for reception. So, implicit in this, that isn't necessarily visible when we look at just the block diagram, is that we need knowledge of the phase. And that's what we're leaving now when we leave coherent detection. So non-coherent detection, there's a couple of ways we can do this. Let's start with one way. When we have a cosine omega ET plus some unknown phase, let's say, offset, what I could do is break it into two branches and say I'm going to do a projection onto cosine, I'm going to do a projection onto sine, and therefore one of them, it's possible one of the branches, it could be completely orthogonal to this, and if the phase is turning, I'm not tracking it, the amount of energy could change as it goes into each one of these two branches as I project on to two. But if I square them, if I do the squaring part here, that means essentially I'm going to get a cosine squared plus a sine squared at the end, because I sum them up over here. So when I sum them, that means that I'm always going to have energy. So if the phase is turning, and sometimes there's energy in one branch, sometimes there's energy in another, sometimes it's split between them, depends on what the phase offset is. Using this approach, I can be sure that I always get energy, because I'm going to take the energy from each one of the branches. So that's one approach. But an even less expensive approach, this approach, I avoid using the phase-locked loop. I don't have to track this phase, because no matter what the phase is, I'm going to get energy out. But another way to do it is to do something that's more straightforward in terms of just detecting the energy. And maybe this will be an even less expensive structure than this non-coherent version. So this is a structure we typically see being used with M-FSK when we do non-coherent detection. Remember, each one of these different symbols is a different, well, I guess I should put in here that it's an unknown phase, because that's sort of the whole reason for this. So each one of these symbols looks like this, right? It's each in a different frequency. So what I can do is I can take the signal, split it, and put it through a filter bank. And the filter bank is centered on each one of the frequencies that I use for my symbols in M-FSK. So here's symbol 1, a filter that just looks for symbol 1, filters out all other frequencies. Here's frequency 2, which is reserved, and all of the other frequencies are rejected. So I take this, and the next thing I do is an envelope detector. Now remember, what does frequency shift keying do is that, let's take the binary case, the simple one. If I have just two, suppose I have just two symbols. So now here is my data that I'm sending. I've got a logic 1001, for instance. So when I transmit it, I'm going to put in, maybe the higher frequency for the 1 and the lower frequency for the 2, for the 0, not the 2, lower frequency. That should be a nice smooth one. And then when I get here, I'm going to go back to the higher frequency. And so when I filter out, this one is just going to see the zeros, and this one is just going to see the logical ones. So the next stage I need is an envelope detector that takes these frequencies and returns them to this square wave. And so to do that, we use this envelope detector. So an envelope detector is a very simple, inexpensive circuit that, for instance, here's a circuit you may have seen in one of your circuit classes. And the idea is that we tune the R and the C. And so in our case, it would be tuned to the bit rate that we're using. And essentially, it eliminates all of the high frequency components, so that when we're coming out of, let's say, we're looking at the output for this logical 1 filter, then it's going to take this, and it's going to be a nice high signal, because we look at the envelope here, and it'll be high. And now when this one comes, filter bank for logical 1 is going to have nothing at the output, because there's going to be no energy in it, so it's going to be 0. Then when this bit appears at the same frequency that I'm looking for with my filter bank, the envelope detector is going to take these oscillations and turn them into a nice square wave. So the idea of this combination of filter bank and envelope detector is to return us from this, except we've separated out, and we'll have one set, which is the logical 1. The output from filter 1 will look like this. And then the outlook from filter 2 is going to look like filter 2, which is looking for zeros, is going to look like this. So let's continue with the binary phase shift keying example, and we're going to look at the error probability. I said that the error probability was directly a function of the receiver structure that we had chosen. So now we're going to see with this new choice how we're going to do the analysis of the error. Now, one thing that's really difficult in non-coherent detection is that we're no longer dealing with additive white Gaussian noise. Because when I filter that noise, it's still Gaussian, but when I put it through an envelope detector, the statistics of the noise are modified, and they're no longer a Gaussian. We've operated with some function onto this Gaussian, and it becomes a different density. The densities that we're going to be looking at are the Rayleigh and the Rice density, and I'll show you them now. But the important thing to realize is that when we look at filter 1, the output, if I actually send S1, if I'm actually sending symbol number 1, that this, which is sent on frequency 1, then my test statistic, what comes out of my envelope detector, is going to have a part which is, of course, related to the presence of the symbol, because I sent S1, so the energy is there, plus there's going to be a component from noise. Of course, if I sent S2, then the output here would be just noise. Now here, the output of F2, when S2 is sent, of course I have energy plus noise. So here, we have two statistics, and depending on which is occupied, one will be noise only, and the other one will be noise plus some energy, which is the symbol that is present. So my strategy, when I use this kind of structure, is to choose the largest at the output. So and remember that I showed that, let me go back to that same example. So here I'm setting logical 1, 0, 0, logical 1, and I'm going to call this logical 1 and this logical 0. Now, when I look at the output for the test statistic Z1, which is looking for a logical 1, is going to have an output that looks like this. That's what's coming here at Z1. Instead I look at Z2. When I look at Z2, what's going to be there? Well, it's looking for logical 0 on frequency 2. So it's going to see nothing here, and then it's going to see something there, and then nothing. So you can see that at any instant of time, what I want to do is when I'm sampling here, well, the Z1 is going to be larger, and this one's going to be smaller. So of course I'm going to choose logic 1 transmitted, and so on. So I'm still doing a threshold test, even with this non-coherent detection. It's a threshold test, but I'm looking at these two statistics. So in one case, it's going to be noise only, and the other case, it's going to be noise plus some offset due to the presence of the signal. So there's these two situations, one where there's noise only and one where there's signal plus noise. Let's look at when there's no signal, when there's really just noise. When it's just noise, I just have additive Gaussian noise, and I know that when additive Gaussian noise goes through an envelope detector, it comes out with a Rayleigh distribution, so it becomes Rayleigh noise. And the Rayleigh noise is given by this probability density function. So in this case, the output statistic, Z1, will be Z1 divided by some variance, sigma squared, and then the exponential of the negative of Z1 squared divided by 2 times the variance. So you can see it looks like Gaussian here, except the Gaussian would not have the Z1 multiplying it. So that's the difference. That's the Rayleigh. And Rayleigh is only defined for positive values. So Gaussian noise can be negative, but of course the envelope detector forces everything to be positive. So of course the probability density function is 0 for negative values. Now remember, this is a conditional probability I've stated because I'm supposing that I'm looking at Z1, the output, but when S2 is sent. So when S2 is sent, there's noise only. Of course, if I'm looking at the output here at Z2, well, when Z2, at the output Z2, when S1 is sent, of course it's noise only. So I have two conditional probabilities, and it's when I'm looking at one, but the other one was sent. And in this case, it's a Rayleigh distribution. So what happens when I'm actually looking at the branch where the signal is present? Then I have signal plus noise. Well, when I have signal plus noise going through a Gaussian noise going through an envelope detector, the output has a Ricean distribution. So the Ricean distribution is given by the density I showed here. And there are a couple, there's an extra parameter that appears. Before we only had the variance. And now we have another parameter, mu. And this parameter is related to the energy in the signal. So EB is the energy in the signal, so it's somehow related to that. And so the stronger the signal is, the larger this value of mu is going to be. So how does it appear in this density function? First of all, it looks kind of like the Rayleigh function, except that I've added in the exponent here the plus mu squared, but I'm also multiplying by this Bessel function. And in case you've forgotten, this is the zero order Bessel function defined by an integral. And here we have this Bessel function, and the argument of it, we've got both our mu here and our sigma squared in the denominator. So it won't be any surprise to you that this mu divided by sigma squared, this part is related to the signal, and this part is related to the noise. And so I have a ratio of signal to noise. And so this ratio, which appears here and sort of appears here also, is going to tell us, how much is on our side. If the SNR is really high, if the signal-to-noise ratio is really high, how is that going to help us in our detection? And we can see we're going to be able to view it directly in this probability density function. Although it doesn't seem very obvious to you now, I'm going to show you some plots that'll make it a little clearer. So let's start with the plot of the Rayleigh PDF. So if I think of K as this mu over sigma, as this quantity, which is the signal to noise ratio. I think before I didn't put the square over the mu squared, sigma squared. Anyway, what I really mean to say is that mu over sigma is related to the signal to noise ratio. I'm going to call that a parameter K. And I can think of the K as going to minus infinity. And if I went back to my equations, here if I put in K equal minus infinity, you would see that the Rice becomes the Rayleigh. So it's one where Rice, if I go asymptotically as I let K go to minus infinity, this Ricean expression would actually become this Rayleigh expression. The I0 would disappear, the second term would disappear. So that's why the two are related. So I labeled this curve K equal minus infinity, but basically it's the Rayleigh distribution. You can see that before 0, there's 0 probability. It's got to be positive. And then it comes up and it's fairly close to 0. Now, as I increase the signal to noise ratio, as I increase K, you can see that the Ricean distribution is getting farther and farther away from the Rayleigh distribution, which intuitively makes sense. If it's small, if the signal is small, then it's still looking like noise. I'm probably still going to be here. The stronger my signal is, the less it looks like the distribution of the noise, and the more it looks like it's being pushed away from the 0 value. So if I were to look at the means of these two distributions, you can see that the means are getting farther and farther apart the stronger the signal is. So let's just, I'm going to take you quickly through the math. Okay, so let's start first with the conditional densities. We said that Z1 conditioned on S1, so this is why I'm looking at the filter output of the filter where the symbol's present, it's Ricean. If it's the other way, that I'm looking at the filter output for where the signal wasn't sent, it's Rayleigh, these two cases. And then here, of course, is the other case, which is Ricean. So I have these 4 conditional probabilities, which represents everything that could happen. I send S1, and I look at what happens in Z1, or I look at what happens in Z2. I send S2, and I look at what happens in Z1 or Z2. So all the possibilities. So I have all the conditional probabilities that I have to worry about. So now I want to calculate what is the bit error rate for this binary system. So I know that there's 2 kinds of errors. I can make a mistake when S1 is sent, or I can make a mistake when S2 is sent. And so the total error, or the 2 types of errors, so it's 1/2. I'm assuming here this is the prior, and here, these are the priors. So I'm assuming here that they have equal priors, that the probability of each symbol is equal to 1/2. So I have these priors, and I multiply by the probability of making a mistake. Now when I send S1, when am I going to make a mistake? Well, I'm going to make a mistake when the output of the wrong filter, Z2, is actually bigger than the output of the right filter. I don't expect that to happen, but every now and then it will. That'll make an error. And then in the other case, it's the other way around. I've sent S2, but somehow Z1 is still greater. 2 types of errors. Now, we've seen the symmetry. These 2 conditional probabilities, they look exactly the same. They're like mirror images of each other. So I really don't need 1/2 of one plus 1/2 of the other, because it's going to give me just 1, because these 2 are equal. So 1/2 plus 1/2 gives the same thing. So I only have to look at 1, just by the symmetry of the case we're looking at. Okay, so now let's look at this one, and how can I analyze this? Well, the way I'm going to analyze it is I'm going to use conditional probabilities. And I'm going to say that if I condition on, I take this, and I condition again on Z2. Okay, I'm going to take this, I'm going to condition on Z2, but I have to average over Z2. So here this integral over dz And this argument here, this is the probability density function. So if I want the total probability, I condition and I average on the conditional probability. So that's what I'm doing here. I take this, condition again, and then average over the whole thing. Now, why did I do this? Because now I have something I know. This I know. This here is a Rayleigh distribution. I know that one. And now let's look at here. Well, now Z2 is fixed. Here I have two random variables. I have Z1 and I have Z2. And I have like the probability that one random variable is bigger than the other. That's a tough problem. Here I've conditioned on Z2. Z2 is now just a number. So now I just have, what's the probability that this Z1 is greater than that number? And that number is Z2. So it's conditioned on Z1, on S2 having been sent. So I know S2 was sent. I'm looking at filter 1. So I know that it's noise only because S2 was sent. And I'm looking at the filter for S1. So it's only noise. So I know it's Rayleigh. So this one is Rayleigh. And this one is Rice. And I have these two density functions. So I've taken the general expression for probability of error, and I've used a little bit of manipulation, exploiting some conditional probabilities to end up with an expression where I know the probability density functions that I have to plug into these equations. So I've repeated it here. Here's our formal equation. And again, first integration over a Rayleigh over an interval from Z2 to infinity, because I had to have Z1 greater than Z2. And now I am taking that result and I'm averaging over the conditional probability, which is a Rayleigh. So now I plug in these different densities. Here's the Rayleigh one with a Bessel function here. And here's the Rayleigh one, integral here. And now, I'm not going to do the rest of the math, but I think it's kind of fun because this looks impossible, right? Wouldn't you love this on your calculus exam? Looks like it's impossible to do, but actually change to polar coordinates, do some simple substitutions, and you will be amazed to find out that it simplifies to a very simple expression. So we find out that this probability of error we're looking for is just the exponential. And the exponential is related to this mu squared over 4 sigma squared, which, if we plug in the values for with this, becomes EB over 2n 0. So this is an expression we've seen before. Instead of having the Q function, which we've always found when we had a Gaussian density, now we have an exponential because of this different integration, but a very simple expression. So we have found the bit error rate for the non-coherent receiver. Here's the expression for the probability of error. We can compare that with the performance of our coherent receiver. Here we have this Q function. So the Q function has an exponential decay, which is can be easily approximated in a certain regime by also an exponential, decaying exponential. So it's easy to find that asymptotically, the difference between these two performances comes out to be about 1 dB. So 1 dB is a very, very reasonable compromise in terms of the required signal quality to achieve a given probability of error, if I can completely avoid the use of a phase lock loop. So this compromise is one that's often used, and it's very rare that we're going to see coherent FSK. It's just not worth all the complexity in order to get 1 dB better performance. So I'd like to summarize now, just comparing the binary cases of the two coherent and non-coherent that we've seen so far. So the very first thing we looked at in the course was binary phase shift keying, antipodal signaling, and we got this waterfall curve for the first time, and this is really our baseline for performance. Remember, BPSK and QPSK pretty much fall on the same line, and therefore that's become our standard, our gold standard for comparison. Then I showed you that you could use a simpler receiver for DBPSK, and in this case, the loss, if we look asymptotically, so you see the loss up here could be more than a dB, but if I look down here, we're looking at something on the order of a dB. So again, a very good compromise. These two curves are not too far apart. Remember, 10 to the minus 2, 10 to the minus 3, these are pretty bad performances, but when we're getting down below 10 to the minus 3, this is where we're looking for our system to be performing. And it's in this regime where the loss is only around 1 dB. So a very good compromise to use differential. This is for BPSK. I would say that in commercial systems, it's QPSK, which is the most effective. It's really good at all 4 hits on performance, spectral efficiency, and complexity. So you would see the QPSK versions of these two, whether it's coherent or non-coherent, and because it's a very good compromise. Now, just to say, we also have the option of going with frequency shift keying, and we'll see later that this is going to be a very good compromise in certain situations with spectral efficiency. So FSK is also very popular. And we first looked at binary FSK, which is coherent detection, which is this curve here. And then, of course, if we moved on to the non-coherent, we saw that the performance was very similar. And in fact, if you want to compare DBPSK with BFSK, non-coherent, these two non-coherent ones, you'll see they're almost the same. There's just a factor of 2, which of course is why there's 3 dB between this blue and green curve. So remember, there are many, many systems out there, each one having its own requirements. Each one has its own requirements to balance the 3 things we're worried about. Bit error rate versus SNR, let's call it EB over S0, the cost, and the spectral efficiency, which we really are getting to very, very soon, because I had to describe non-coherent to coherent before I could start talking about what the choices we're going to make are going to have an impact on the spectral efficiency.